Hi everyone, today we're going to look briefly at the first derivative test for maximum and minimum points. First thing we're going to note is that maximum and minimum points are also known as turning points. So if you're on a curve and you're going up and you hit a maximum point and then you turn and you come back down, they're also known as stationary points because for that split second, if you think of a pendulum, if it's swinging to the right before it turns to start to swing back to the left, it's stationary. Just for that split second, it's stationary, and then it comes back down. So that's the kind of concept behind turning points and stationary points. Also remember that when we speak of the first derivative, we're talking about differentiation, differentiating a function. So if we think of a curve, y is equal to something. If we differentiate, we get dy dx. Or if it's a function, we'll say f prime of x. And remember when we speak of differentiation, that first derivative gives us our gradient function. And of course the gradient is a slope. And it's a gradient function because when we're dealing with anything other than a straight line, the gradient or the slope is dependent on the particular point of the curve that we are looking at. So let's start by looking at a simple quadratic. Okay? Now we are interested in the minimum point, the turning point, the stationary point, and in this case it is a minimum point right here. So if we're talking about the first derivative and we're talking about the gradient, well, what is the gradient at this minimum point? Well, there's a tangent. It's a horizontal line. The gradient, if you recall, is you change in y over change in x. So what is the gradient of a horizontal line? Well, it's 0, which means therefore that the gradient function dy dx is equal to 0 at this minimum point. Same goes for my maximum point. Here's my tangent at the maximum point here, and the gradient function dy dx is equal to 0 at that maximum point. Sometimes you may have a curve that has more than one turning point. Here we go. This curve has a turning point, a maximum here and a minimum here. And at both, dy dx is equal to 0. So how can we use this information? We see that whether it's a minimum point, a maximum point, or whether we have both, the gradient is a horizontal line, and therefore the gradient function is equal to 0. Okay, so let's take our first example. And suppose we are asked to find the coordinates of the stationary points. And of course, we have the graph here to help us, and we can simply read the stationary point coordinates off. But let's say that we were given the equation of the curve. Y is equal to x squared minus 10x plus 27. We know that the gradient function is equal to 0 at the maximum or minimum point. So we say, okay, let's find the gradient function. So dy dx is equal to 2x minus 10. And at the maximum or minimum point, dy dx is equal to 0. So we say, okay, that means that 2x minus 10 is equal to 0. Because remember, this is my dy dx. So here I go, dy dx is equal to 0. Therefore, x is equal to 5. There we go, x is equal to 5. We put x is equal to 5 into our original curve to get our y coordinate. So we get our 5 squared minus 10 by 5 plus 27 is equal to 2. And therefore, we have our minimum point of 5, 2. Now, the thing is, there's a little trick here. Remember, the gradient function is equal to 0 at the maximum or minimum point. So how did I know it was a minimum point? Well, because I make the connection, I make the link. I know that this is a quadratic, and I know that once my coefficient of x squared is positive, I have a minimum point. Plus, of course, I have the graph here to help me. Let's try this one. Same question. Find the coordinates of the stationary point. In this case, y is equal to negative x squared plus 4x minus 1. So dy dx will be negative 2x plus 4. And again, at the maximum or minimum point, the gradient function, dy dx, is equal to 0. Means negative 2x plus 4 is 0, and x is equal to 2. And we plug it into y, and we get a y coordinate of 3. Therefore, our maximum point is 2, 3. It's your turn. Turn to Tulsi and try these 4 questions. Now, note, all I want you to do is simply state whether the turning point is a maximum or minimum based on your knowledge of quadratic curves. If the coefficient of x squared is positive, you know you have a minimum point. If the coefficient of x squared is negative, you know you have a maximum point. I've written them out here for anyone who may not have the text. Okay, now, what about if it wasn't a quadratic curve? And what if we weren't able to easily determine, just by looking at a coefficient, whether the turning point or the stationary point in question was in fact a maximum or a minimum? Well, let's look at this original graph, this first curve that we looked at again. If we look, this is our minimum point here, and this is the x coordinate. If we go just a little bit to the left of this coordinate, let's say we go to 4, and we come up here. What's the gradient at that point? There we go. Let's take an out tangent. Is that gradient negative or positive? We've got a negative slope, right? And what about if I went a little bit to the right and I wanted to get the tangent here where x is equal to 6? In this case, I now have a positive slope. Well, we're going to use this information to help us determine whether a turning point is a maximum or a minimum. Let's look at how. Okay, so I've put the little graph here, the picture, so that you can see for this first example. So y is equal to x squared minus 10x plus 27. And we have to find the coordinates of the stationary point and determine its nature. That is, determine the nature of the stationary point. We have to say whether it is a maximum or a minimum point. So we already did all our dy dx is equal to 2x minus 10, which would be equal to 0 at the turning point. That means that x would be 5 and y would be 2. So we know the coordinates of the turning point are 5, 2. So let's say we did all that. What we want to do next is we want to set up a little table. We want to set up a table of values of x and of dy dx. And the first value I'm going to put in the center here is x is equal to 5. And why is that? That's because that's the value of x that makes dy dx equal to 0. Then let's choose a value that's less than 5 to the left of the turning point. Remember, I don't know at this point whether it's a maximum or a minimum. I'm actually going to choose the number 4. Okay? If I say x is less than 5, and let's say x is equal to 4, when x is equal to 4, dy dx would be equal to 2 times 4 minus 10, which would be equal to negative 2. That means dy dx would be less than 0. Now, how about I choose another number to the right of x is equal to 5? Okay, so I want some number where x is greater than 5. And I'm going to get the result in this case that dy dx is greater than 0. And I mean, we can try it. Let's say x is equal to 6. Then dy dx would be equal to 2 times 6 minus 10, which is equal to 2. Indeed, it is greater than 0. So what does that look like? It means that I've got dy dx is negative to the left of my turning point, and it is positive to the right of my turning point. Well, what would the slopes look like? A negative slope comes down. At 0, I know I have a horizontal line, and a positive slope goes up. Therefore, 5, 2 is a minimum point. I hope you can actually see that. It's kind of modeled out here for us. Here, see? Comes down, stationary, and goes back up. A minimum point. Let's try a question now where we don't have a graph. Okay, so given the function f of x is equal to x cubed minus 4x squared minus 3x plus 8, we've got to find the stationary points, and note the use of the s here, and then determine the nature of each point. So I know that I have a cubic graph. Okay, it's an x cubed. It's a cubic function. So let's take the first derivative. So f prime of x is 3x squared minus 8x minus 3. And at the stationary points, f prime of x is equal to 0. Our gradient function is equal to 0. That means that 3x squared minus 8x minus 3 is equal to 0. This is a quadratic, yes? So what do I do when I have a quadratic? Well, the first thing I'm going to try to do is factorize. Unfortunately, this easily factorizes into 3x plus 1 multiplied by x minus 3. That's equal to 0. It means that x is either equal to negative 1/3 or 3. So, when x is equal to negative 1/3, I plug the value, sorry about that, into my y, and I get my y value of 8 and 14 over 27. And when x is equal to 3, plug it in again to the function, I get y is equal to negative 10. So these are my coordinates, my x and y coordinates. All right? So I've got my function. I've got my gradient function or first derivative, which nicely factorized. And I've got my stationary points. Negative 1/3, 8 and 14 over 27, and 3, negative 10. So I've got to determine which of these points is minimum and which is maximum. Because you see, if I have a cubic curve, one has to be minimum and one has to be maximum. Okay, it's going to turn twice. So let's start with our first point. And let's set up our table. So we've got x. We want the value of x that gives our f prime of x equal to 0. So x is equal to negative 1/3. F prime x is equal to 0. Let's try x is less than negative 1/3. So I'm going to go with negative 1 for x is less than negative 1/3. And I'm going to go with 0 for x is greater than 1/3. Here we go, negative 1 and 0. Okay? Well, when x is negative 1, I'm actually going to plug these values into this. So it'll be 3 by negative 1 plus 1. Well, that's negative. And then negative 1 minus 3. I'm going to have a negative multiplied by a negative, and that is positive. Remember, I don't actually care what the value is. I just care to find out whether it's positive or negative. And then what about 0? 3 times 0 is 0. So I'm going to add 0 plus 1, that's positive. But 0 minus 3 is negative, so I have a positive by a negative. So I have got a negative. So what does that look like with the slopes? I've got a positive slope going up, negative, a 0 slope, and then a negative slope coming down. So what does that look like? What does that look like? Here we go. So this has to be a maximum point. Now, you could set up the same table and do something similar for the second turning point, 3, negative 10. So you'd have, in the middle here, you'd have x is equal to 3, and maybe to the left you'd have x equal to 2, and to the right you'd have x equal to 4. But I would be very disappointed if you did that, because we already explained that if it's a cubic curve and it has 2 separate turning points, if one is maximum, the other one must be minimum. So a perfectly valid explanation would be to say, since a function is cubic, the other turning point, 3, negative 10, must be a minimum point. Okay? Your turn. Go to Tool C and try these 6 questions. I've written them out here for you just in case you don't have the book. Get them all done before class and when we meet again. And remember, mistakes are proof that you are trying. So write it down. Don't bring me a blank page and say, I tried it, but I put it on a scrap piece of paper. But also remember, please don't keep making the same mistakes.